Today we're going to talk about abstract vector spaces. And the concept of an abstract vector space is to split up the notion of what vectors are, which so far have been ordered pairs or triples, or more generally ordered n-tuples of real numbers, from what we can do with vectors. So we've seen that the fundamental operations with vectors are to multiply them by scalars and add them together. And to introduce this idea of abstraction, I want to suggest an analogy with chess, which is that when you play chess, you can ask a question like, what is a knight? And the answer is a piece of wood carved into the shape of a horse or something like that. But you really don't care actually about what a knight is. What you really care is what you can do with the knight. And in the context of the game of chess, what you can do with the knight is move it in an L shape like that. And that's really the essence of what a knight is about in the context of the game of chess. You can change the form of the knight to look very different, and you haven't fundamentally changed the game. So let's talk about an example of a concept that we've developed that really doesn't make reference to the nature of the vectors at all. So this is the definition of linear independence. It says that if we have a linear combination of some vectors equaling 0, then all of the weights in that linear combination had to be 0. So that is a statement which is true if and only if the sequence of vectors from v1 up to vn is linearly independent. And notice that in order to make sense of this definition, it really doesn't matter that the v's are ordered tuples of real numbers. What matters is that we know how to multiply each vector by a number, and we know how to add vectors together. And we also need a way of picking out what the 0 vector is so that we can check when we've worked out what the left-hand side of this equation is, whether it's equal to the 0 vector. Okay, so a vector space is going to be an abstract set, meaning that we're not saying anything about what's in the set. It can contain arbitrary types of mathematical objects. We don't care what these elements of this set look like. But what we do care about is that we have an operation plus and an operation times that are satisfying certain properties. And I'm just going to list all these properties here at once. So the first thing to say is that the vector addition operation, the plus sign, is something that you do with two vectors and you get another vector out. So that's the condition described here by number 1. If you add two vectors, you get another vector in your vector space. In other words, just another element of this set V. The multiplication operation takes place between a scalar and a vector, and it gives you another vector back, just like with vectors in Rn that we're already familiar with. And that's what line item number 6 says, that if you multiply a vector times a scalar, then you get some element of your set V. In other words, you get a vector. The rest of these conditions are just things that you need the operations to do to play nicely with each other and behave well. So for example, you really want vector addition to be commutative, that's number 2. You want vector addition to be associative, that's number 3. you want there to exist an additive identity, that's number 4, so a vector which we'll call 0, which has the property that if you add it to any vector, you get the same vector back. You also want there to exist additive inverses. So for every u, there's some other vector v, which we'll call minus u, suggestively, with the property that the two vectors add to 0. So that's number 5. Number 7 says that scalar multiplication has to distribute across vector addition. Number 8 says that scalar multiplication has to distribute across scalar addition. Number 9 says that the product of two scalars in a vector has to be associative. So if you multiply first by one scalar and then by the other, that's the same as multiplying by the product of the two scalars. And number 10 says that if you multiply the number 1 by times a vector, you get the same vector back. So to be clear, the way this is going to work in practice is that an example will have to consist of a set V and some operation which we call plus defined on V, and some operation we call times, which tells us how to multiply elements of V times real numbers. And that set and those two operations are going to be required to satisfy all of these conditions in order for us to call it a vector space. So there's some conditions that we want that are not in that list. So for example, you want to be sure that if you multiply the scalar 0 times any vector, then you get the 0 vector. But actually this follows from the conditions that are already listed. For example, we can prove it by writing 0 times u as 0 plus 0 times u. That's true because 0 equals 0 plus 0. And then we can use the distributive property of scalar multiplication across scalar addition to write that as 0 times u plus 0 times u. So here we have an equation that says that one vector, 0 times u, is equal to that same vector plus itself. That means that we can subtract 0 times u from both sides. In other words, add the inverse of 0 times u to both sides, and we find out that 0 is equal to 0 times u. So there's some other natural things that you would want that follow from the 10 conditions we already listed. So one of them is that if you multiply the 0 vector by any scalar, you get the 0 vector. And the other one is that if you want to calculate the additive inverse of a vector, then you can just multiply -1 times that vector. So both of these can be proved in a manner similar to this proof that we just gave. And the third one is that additive inverses are unique. So if you have two vectors, both of which add to some other vector to give 0, then you know those two vectors have to be equal to each other.